These pictures are actually more rigorous mathematics than you find in any standard quantum textbook.
What does your crystal ball say about when we can expect to have a real application do better than classical computers could do?
As with many things in science and in the world, you can look at things with different pairs of glasses. And what we have provided is kind of a different pair of glasses to look at a quantum world.
What are some widely embraced myths or misperceptions about quantum? I know that we had a conversation last week, and you told me, if I got this right, it's not true that a qubit can be a 0 and a 1 at the same time.
A lot of people in industry start to come up with new capabilities of quantum mechanics. And the idea of quantum computing was put forward by Feynman. And then suddenly people started to think about quantum mechanics not anymore as this weird, ugly formalism, but in terms of an interpretation as processes. What can we do with these processes?
From Orion X in association with Inside HPC, this is the At HPC podcast. Join Shaheen Khan and Doug Black as they discuss supercomputing technologies and the applications, markets, and policies that shape them. Thank you for being with us.
Hey Shaheen, great to be with you.
Excellent to be here, and once again, I'm really excited about this session.
Yeah, me too. We have a luminary of the quantum computing field. He is Bob Coecke. He is a theoretical physicist and logician who was a professor of quantum at Oxford University until 3 years ago, when he became chief scientist at Cambridge Quantum Computing. And after that company merged with Honeywell Quantum Systems, he's now chief scientist of Quantennium. So it's very interesting. Bob teamed with Dr. Stefano Goggioso. He is a mathematician and computer scientist with a PhD from Oxford, who actually he was a student of Bob's. Dr. Goggioso is now a lecturer on quantum at Oxford. He's also the co-founder of a company called Hashberg, a startup where he directs development of quantum programming tools. Now, Bob and Stefano have written a new book. It's available on Amazon. It's called Quantum in Pictures. It has one of my favorite pieces of cover art that I've seen recently, and we can explain that in a minute. But Quantum in Pictures is intended to provide a simple, straightforward way of teaching everyone what quantum computing is in an accessible and more inclusive way. So, Bob, it's a pleasure to have you today.
Thank you. It's good to be here.
If I could just kick off our discussion, as I think 99% of the population knows, quantum mechanics is very difficult for most people to understand. Why would you say that is, Bob? And how did you arrive at the idea of using pictures to help people improve their understanding of quantum?
That's a very good question. There's a few problems why it's difficult to understand. First of all, the mathematics has a high entrance fee. You don't learn this in high school. You have to go to university. And actually, you have to go not to first year, second year university, but it's typically third or fourth before you really get enough maths to really understand what's going on. Another problem with quantum is that it is sort of an abstract formalism. It's given as an abstract formalism, which you use as some sort of kitchen recipe rules, which basically tell you how you compute things and how you get numbers out of it. Now, people have tried to assign meaning to these recipes, but everybody disagrees. There's been disagreement for 70, 80 years and contradictory views. And some people get pretty angry and, and annoyed about other people's views. Now, let's just go back to the formalism. So the formalism basically does tell you something about what quantum is, but you need to understand the math. You can't just simplify it, because if you simplify it, you say wrong things. So that's part of the problem. Now, as with many things in science and in the world, you can look at things with different pairs of glasses. And what we have provided is kind of a different pair of glasses to look at a quantum world than what was initially provided. I mean, this is about high performance computing, so about computing. So the traditional formalism of quantum mechanics was provided by John von Neumann, the father of the modern computer architecture. So people may not know this, but he's also the father of the formalism, the language which we use to talk about quantum, the mathematical language. But interestingly, 3 years after von Neumann published his book on the language of quantum, or the formalism of quantum, he denounced it himself. He basically said, this is not the right way to do quantum. It just happens to work, but it's really not the right way. I mean, to make a comparison, initially computers were programmed with zeros and ones. You basically typed zeros and ones, and that was your program. Nobody uses this anymore. This is not the right language to program a computer. And similarly, von Neumann felt that the language he came up with was not the right language to talk about quantum. Now, I didn't wake up one day and say, okay, I want to simplify the way we talk about quantum. That's not how it worked at all. What I did wake up was a supervisor and an academic grandfather who were telling me quantum mechanics is not right in the way it's taught. Like, not, he was right, but the formalism was not right. We need a new formalism. Listen to von Neumann. He told us that. That's what I was told. So I basically was looking for another way to look at quantum, a more natural, not having in mind whatsoever that it actually would be simpler or that it actually would even involve pictures. That was actually an accident because initially I went much more difficult than the usual formalism. I went very abstract into a field called category theory, which is pretty much considered as the most abstract mathematics around. It's mathematics about mathematics, basically. So it's really abstract. And the first paper in this line of work was called A Categorical Semantics of Quantum Protocol, and most physicists weren't able at all to read it. It was too difficult for the professionals. But then by some weird twist of whatever, if you go abstract enough, then suddenly it becomes very simple. And in the 70s, here in Oxford, there was Roger Penrose, who most people know because he got the Nobel Prize and he writes popular books and all that. And he started to draw pictures in the 60s and the 70s. He started to draw pictures when he was studying at university general relativity, and he didn't like the symbolic representation. So he realized that equivalently, you could actually represent things in general relativity, which is super complicated too, with pictures. And then in the 90s, two smart mathematicians, they actually proved that certain kinds of category theory, which happen to be exactly what I was using, are equivalent to drawing pictures. So these pictures are actually more rigorous mathematics than you find in any standard quantum textbook, which is the weird thing. I mean, I've already had reactions from physicists which look at our book and they say, man, that looks like, that can't be serious. That can't be serious. It looks way too silly and childish, but it's actually more rigorous and abstract mathematics. So basically, we wanted to come up with a new formalism of quantum mechanics, which then ended up looking like pictures. Now here, it took a really long time to get rid of the category theory. And this is a sociological thing. You know why? I mean, I was a physicist. I was trying to get a career in academia. And by some weird twist of fate, I ended up in a computer science department. And also, what I was doing, physicists were pretty conservative against it. And the way I would get an academic position was by publishing in computer science journals. And to get your papers published, you had to use category theory. You couldn't just draw pictures. So even though I felt I wanted to draw everything in pictures for a long time, just for career reasons, we had to make it look more complicated than necessary. It's different in different disciplines. But then, so the first, at some point, I was so fed up with having done all that work, and even the physicists didn't accept it because it looked too difficult. And then I wrote a previous book with Alex Kissinger, also a former student of mine, also at Oxford University, computer science. And this was called Picturing Quantum Processes, and it's now informally called the Dodo book. It's much thicker than the new one, and it's not written for inclusivity for a general public. It just explains to the physicists how what they know relates to diagrams. But then when we were finished with that one after 3 years, I felt we really now need to also write a book that basically shows that you don't need to know any maths to know this stuff, and that everybody can actually learn quantum mechanics and the basic principles of quantum mechanics through this new language. But it is a very different perspective on the usual presentation. I mean, philosophically, it's a completely different angle on physics in general than what is usually done.
So we had Feynman diagrams a little earlier than when Penrose did his. Are these all related? Are we building on top of each other and it's the same kind of a concept, or is that a different fundamental direction?
That's a very important question. So Feynman diagrams, they were introduced to guide you into certain calculations. So you work with the usual quantum mechanical formalism, which was still built on von Neumann's. And then Feynman diagrams, they tell you how you specifically do your calculations, but they can't live on their own. There is no such thing as like the Feynman diagram formalism or language of quantum mechanics. It's like their existence needs the usual quantum mechanics. With our stuff, it's different. They can live without the usual quantum mechanics. And then, I mean, this is, while the book may look very easy, there is, if you look at some of the research paper, there's pretty hardcore. And a bunch of former students of me, they have proved that any equation you can derive in the usual language of quantum mechanics, von Neumann's, you can also derive with the pictures.
So you have a complete mapping to each other.
You probably didn't know, but you use the exact technical term, completeness. It's called complete. In logic, this is called completeness. If you come with a system, a reasoning system, in which you can prove everything about your model, that's called a complete
Excellent.
system. So, indeed.
I can stop the podcast now because I got that right.
But while you're ahead.
But relevant to this, Bob, a question is, and this was part of my motivation, is the fact that we are now using quantum mechanics as a basis for computing, which means we're not just observing and we're actually trying to make it programmable and manipulatable and directed towards a particular solution. Does that have an impact on how we perceive it and how we visualize it?
Completely. So basically, what quantum computing did from the early days onward was thinking differently about quantum mechanics. For a long time, people had been perceiving quantum mechanics as this is just weird, and how can we avoid it? Some people really didn't want it, and they were basically trying to come up with theorems and stuff against it, trying to disprove. But then, like in the 80s, people like Charlie Bennett at IBM, they basically said, okay, what can we do with it? And then people started to come up with protocols like what was called dense coding, like how you could actually compress information. That's something Bennett and Wiesner did at IBM, both, I think, at a time, and quantum cryptography, in which Brassard was also involved in. So people in the 80s, and typically people in industry, by the way, a lot of people in industry start to come up with new capabilities of quantum mechanics. And the idea of quantum computing was put forward by Feynman around the same time. And then suddenly people started to think about quantum mechanics not anymore as this weird, ugly formalism, but in terms of an interpretation. Okay, we think of quantum things as processes. What can we do with these processes? So the philosophy changed a little bit. So there was this process thing coming in. And basically, our formalism with the pictures is a process formalism. On a very general level, the sort of diagrams we use can be seen as the most general language you can use to describe processes. These don't have to be like physical processes. This can be computing processes. Computing process, that's programs. You got programs, they take in that data in, they put data out. You can compose programs like modules into bigger programs, subroutines, things like that. So this idea of composing things became more and more to the forefront against the usual view of quantum mechanics. And basically that's what we did. We went for a formalism which started from this concept of processes and also how you compose them in parallel, for example. Because at some point, Schrödinger had said that the most important thing about quantum mechanics is what happens if you put two systems together. That they start behaving completely different than if you put two classical systems together. And what happened immediately, like at the start in the 90s, despite the fact that the theory was 60, 70-year old, suddenly people started to come up with a huge pile of new phenomena. By looking different at the theory, like what are the capabilities? I mean, in computer science, they say it like this: it's not a bug. Quantum mechanics is not a bug; it's a feature. And let's see what we can get out. And suddenly, people start to discover so many new things. I must say, like quantum mechanics was a lot of physics is a bit of a macho thing, you know. I mean, when I was a student, I was told if you don't do things in infinite dimensional, you're not serious. You're not serious. Everything has to be infinite dimensional because otherwise the maths is too trivial. In quantum computing, it's all about two-dimensional stuff. And it's exactly this simplification which made people discover so many new things like quantum teleportation, the algorithms like Shor algorithm, and there's so many of these things people came up with. So totally new ideas of what you can do with quantum systems. So yeah, computing made a big change to it, made a big change and basically made it move forward or in a different direction, I would say, in a completely different direction. People don't really look at the infinite dimensional stuff anymore.
Now, Bob, no pun intended, but from a big picture perspective, what are some widely embraced myths or misperceptions about quantum? I know that we had a conversation last week, and you told me, if I got this right, it's not true, something that I've heard many times, that a qubit can be a 0 and a 1 at the same time. So explain that, but also any other sort of misperceptions about
Yeah. So
quantum.
I would say there is two classes of misperceptions. One is about because just not knowing the exact math that you can't really state what it is. So I can try to explain why the 0 and 1 thing is not true. Basically, a qubit is a bunch of possible states which live on a sphere. They live on a sphere intuitively. And At some point, you got a point of the sphere, and maybe the top is 0 and the bottom is 1. Now, what's going to happen if you decide to ask the question, are you in 0 or 1? Then it will change. Then the state of the system will change to either 0 or 1. But before it was not. It was probably somewhere else. The only time it would be in 0 is if you would get 0 with certainty. The only time it would be in 1 if it would be with 1 in certainty. But the thing is, this is from the perspective that you can only ask one question, 0 or 1. Now, there are different questions you can ask in quantum. Plus, which is sort of the sum of 0 and 1, and minus, which is sort of the difference of 0 and 1, you could ask the question, are you in plus or minus? And that's a completely different question, and then the outcome would be plus and minus, which is a completely different thing than being either in 0 and 1. So you need to understand the maths to basically be able to say what's going on, and that's not a simple thing. That's definitely not a simple thing in the traditional formulation of quantum mechanics. Now, the other problem with misconceptions is that what I said before, people have very different views on quantum mechanics. So somebody will tell you, of course, okay, every time a quantum measurement happens, the world splits up in different worlds. Okay, and some people actually deeply believe that, and some other people think this is the biggest nonsense ever. And then there are some other people who say, well, if you make a choice, if you decide on something, you actually don't decide. This has been determined long before you by nature.
Right.
Some people think that this is serious, and other people think this is complete nonsense. And then other people think quantum mechanics is some sort of twisted probability theory. Okay, and these people disagree, and then they hate each other, and that also causes confusion to people, of course, because these are easier stories to tell. I could say this easy in word without actually making any reference to the maths, but they can be as wrong as they can be right, and people get all these different stories at the same time. So everybody just gets confused. Now, are they myths? I wouldn't call them myths. I would call them dreams or speculations or something like that, or
Right.
whatever, or hopes or something like that. They are not really myths. I mean, people hear about quantum teleportation and they think about Star Trek, and then they think that you can instantly send something from here to wherever, which is not possible because that violates Einstein's theory of relativity. Now, something is going on, and then people call this spooky action at a distance, but it's not really action. So that's another myth, especially with the Nobel Prizes here going to non-locality. Everybody was
Right.
writing about spooky action at a distance, but it's not an action. You cannot from one place act onto another place. That's excluded. That's impossible by relativity theory again.
But there is correlation, right? That's kind of, isn't
That's a
that
very
what we're
different thing.
saying?
That's the correct statement. You obtain correlations that cannot be explained in a causal way, as if something was there in advance that went in two ways. There is there is instantaneous correlation that's being established, but you can't do action from one to the other. So it's very subtle. It's all very subtle. But how do you explain these things? It's very hard to explain this without the right math. Now, we actually, in our book, we explain quantum non-locality using the pictures, and that's because we have this process perspective, which actually makes things which were before difficult to explain quite a bit easier to explain, because we got one picture which tells the whole story from the beginning to the end.
Right. Now, are these questions necessarily binary? Are you 1 or 0? Are you plus or minus? Or can I say, are you?
No, I mean, in the case of quantum computing, everybody works now with qubits, mostly, but there is no reason why we would stick with qubits forever, you know?
Right.
Quantum mechanics initially was about infinite dimensions, like I said
Right.
earlier.
Yeah.
And actually, then you go to quantum field theory and everything is continuous.
Right.
And then people doing quantum optics, they can also create continuous stuff. So in principle, you could have analog quantum computing in the sense that like your questions are actually analog.
Right, exactly. No, we do have a graph that is analog, digital, classical, quantum as a 2 by 2, and that eventually all the quadrants will get filled.
Which graph?
As an industry analyst, you usually have to come up with a 2 by 2 graph.
Ah, okay.
And the 2 by 2 that we came up with a few years ago with some collaboration was a 2 by 2 where one axis is analog versus digital,
Uh-huh.
and the other axis is classical physics versus quantum physics. And then we would say that most computers, traditional computers, are digital classical. But then quantum effects are creeping into those, and then you get analog and classical, and there are those analog computers are there too. And now the bottom half is all quantum, and you can have quantum analog and quantum digital. And those
Yeah.
are also showing up. That's what I was referring to.
Yeah, totally. I mean, there are many different architectures already around. Like, for example, The D-wave thing is intrinsically continuous because it's about an evolution
Yes.
you're trying to sort of do. And the optical quantum computers are quite a bit different. For example, the ones PsiQuantum are doing, or
Yes.
Quandela, or Alexander do, they're quite a bit different from like the ours or
Yes.
IBM or Google. And what's really interesting, I mean, personally, conceptually, the optical quantum computers, they use a very interesting idea, which I think for this particular podcast and your audience will be very interesting. So the typical idea people have about a quantum computer is you got some initial data, your state or something like that. Then you've got your program which you run, which is like a bunch of gates, like a little
Hmm.
bit like a virtual computer, and then you measure your outcome. That's the typical quantum computational model. But early this millennium, two people, Rausendorf and Briegel, they came up with an entirely different model of computing. What you do is you build some huge entangled state of many, many, many particles. Like,
Hmm.
think of some grid which you fill with lots and lots and lots of quantum particles, and they're entangled in a particular way. They're all entangled with each other in a particular way. It's cheap entanglement, by the way. It's not expensive entanglement, but it's highly entangled still. And what you do then is basically you start observing them one by one. You look at
Hmm.
one, you look at the other, you look at the other, but you look at them in different ways. And the ways how you look at them depend on your previous observation. And you can prove that this is universal quantum computational model, that any
Hmm.
computation you can do on the ordinary architecture, you can do like this too. And this is such a big departure about how people typically think about computation. This is computation by observation.
Huh. But that causes the transformation that takes you from one phase to another phase, so to say. Yeah.
So what I was telling about before, when about the question about are these systems in 0 and 1 at time, this is the biggest counterexample to that idea, because the observation itself, the asking the question in a certain way, causes the change of the system depending on which question you ask, and change the state in either the 0 or the 1 or the plus or the minus or whatever you ask. And doing that enough allows you to make any possible computation. And this way of doing things turns out to have a lot of advantages because you can in advance a step. There is no depth to your computation. There is no depth.
Mm-hmm.
It's just like depth one. You got one state in advance and everything gets handled once.
Yeah, so this thread is causing like two or three different dimensions of questions for me, and hopefully I remember all of them. but but one of them is really just the different modalities, so to say. The different approaches is the word I used to use, but I think the industry likes to call it modality. And we have really this half a dozen different approaches to quantum computing, from trapped ions, as you guys exemplified really well, with high fidelity and good quantum volume, and the great progress that you've been making. But then also neutral atoms and photonics and superconducting and on and on. So one question is, where do you see all of that? And have the industry achieved its transistor moment, so to say, where we have one approach that seems to be winning out or seems to be a good horse to bet on? Or are we still exploring?
I mean, it's not obvious that there will be like a transistor moment in the sense of there will be a unique thing. It could be that different tasks, and that's actually already happening now, would prefer different architectures. So let me first explain. There are two different layers here. On the one hand, there is the choice of your physical substrate, which, like you say, could be ion traps, could be like photons, could be whatever.
Hmm.
Your choice of physical substrate. Then there is how do you work with this physical substrate? How do you make sort of a qubit with it? And for example, our computers specifically, the qubits move around. It's not that the gates go to the qubits go to the gates. They're just dancing around. That's what basically the
Hmm.
former Honeywell, while other people doing ion traps, they may do different things. They leave the qubits in their place and then they try to sort of manipulate them in a way when they're still far apart. So that's yet another difference you can have.
Hmm.
And then the third difference is what I was just explaining. What is your computational model? Are you going to do a bunch of gates and then measure? Or are you going to do this measurement based stuff? On our machine, in principle, you can also do the measurement based stuff because we're able to do intermediate measurements. So you can do a
Right.
measurement and then go on. I think we are the only ones you can do this. I'm not sure, but I think we're the only ones you can do this. At some point, we were the first ones, at least. Just to give you an example, you may have, okay, we're now in this NISC era. Things are quite noisy. And depending on what you want to do, you may want to have a lot of qubits and then you would go to an IBM machine or a Google machine, or
Hmm.
you may want to have a lot of depth for your gates, and then you come to ours.
Hmm.
We might have less qubits, but our qubits are much better. And so you can apply much more operations to your qubits you have and still have them like in a decent state. So
Right.
this difference is already now happening now. And for example, I've got one particular task in mind which I want to do. And this is actually much more suitable for our machines than, say, the IBMs, for example. Although
Hmm.
we in principle work with everybody. We are like a hardware agnostic firm. We have good relationships with many companies like so, and then we work with all the different, personally, like as a theorist, we work with all the different platforms together.
Right.
And
Right. So,
I could see hybrids. I could see hybrids.
okay, so that also tells me that we are still sort of in the exploration mode, and there are different approaches that are good for different applications, and
Yeah, yeah.
maybe at some point in the future one finds a way of doing it, etc. But this also leads to a different question, and that is, do you program these different approaches the same way? Do you map it to the same way, even if they may not be ideal, or do they each require a different style of programming?
The way we are handling it, and that's now specifically within our company too, is like we've got this compiler. It's not really a compiler, it's much more than that, which is called Ticket. And that thing does all the work for you. You write your program, and that thing actually then goes to figure out, like, okay, which is the hardware I'm talking to, and what do I need to do in the optimal way to actually put your program on that specific hardware. So when we are doing it, we don't care.
Right,
I mean,
got it.
the main thing we care about is like we can test, okay, we send this program to that computer and we send this program to that computer, and one does better than the other because of, for example, the program is quite deep or the program requires a lot of qubits. So you can't test them against each other, but the compiler does all the work in this, so we don't really
But
care.
that seems like it's a really a combination of the algorithm and the formulation and the hardware and the compiler, so to say, and all of those blend into this is the way to go.
Of course, what you would say is like the thing is the same. Like you use a high level programming language because it's easier to program something. But then if you really want to completely optimize your thing, you may go to a much lower level and try to tweak things so that it goes quicker. And then
Right, right,
of course
right,
that's possible. Of course that's possible. And there are even people now, this is like a new development, which are really considering the physics itself in their programming,
right.
physics of the gates itself. And some people have shown that you can actually improve your results incredibly by doing that.
Yeah, that makes sense.
Because it's a much more organic physics than transistors, of course.
Bob, we've heard there's conflicting views actually on this. Typically, we hear that getting data out of a classical HPC system, say you have classical HPC working alongside quantum, that
Yeah.
it's very difficult to get data from one to the other. Where do you come down on that?
I mean, I don't think it's that conflicting. There is no concept of quantum RAM yet. There is just no concept at the moment. Well, the concept exists, but it's not realized. And maybe the concept isn't entirely right. So basically, the idea, okay, I've got some data here. I'm going to store it and then in my quantum computer and do something. You pretty much lose all the advantage you could within the existing technology. That's just a fact. Some people are working on it, and some people believe that it's going to be there at some point, like quantum RAM. Other people are more suspicious, so that's something we don't know. But we have found new ways to actually get data in a machine, which is again completely different on how you would do it classically. So what most people do now, and myself, we do this too with my team, is like you basically treat your quantum circuit like some kind of neural network and you train it. So you train your gates. You fix your initial state, and then your task is more about the process than the data. So you create a process which can, of course, prepare your data in the way you want it. And in the case what we are doing, it's a lot like dealing with natural language. And for example, for us, a program is a text, is an implementation of a
Mhm.
text. And then we want to learn something of text. So we train the words on the quantum computer, which is completely feasible. And that's what most people are doing now. They're training stuff on the quantum computer. They're training the gate settings. Now, these settings are classical buttons. So it's already a classical quantum hybrid, what people are doing
Right.
there.
So the data streams in like one bit at a time into the quantum computer.
I mean, I think if people would now take some data, like people using machine learning, and try to stick this on a quantum computer, that doesn't make any sense. Like I said, what we do is like we train the text. We actually, natural language processing about assigning meanings in terms of vectors to things. Of course, these vectors in our case are like quantum vectors or quantum gates. And
Right.
we train these meanings just like with large language model. They use like these vector embeddings and stuff like that. We train them on the machine itself.
Now, to what extent does that make it a very special purpose specific thing that is trained just
No,
for?
no, like I mean, the quantum chemists do exactly the same. So one of the biggest applications, widespread applications envisioned, is chemistry and materials, and they're doing exactly the same. This is how they get there. So in their case, the circuit, the program, would be the evolution of a chemical, and then
Mhm.
they train the program such that it effectively mimics the evolution of the chemical. That's what they do. What mostly, and that's actually where the biggest promise is, I think. I mean, people were before talking about factoring algorithms and search algorithms, but where the biggest promise is now, I think, is simulation algorithms. So
Yes.
and so you basically train your program to mimic the simulation. In our case, I mean, we've got a very, very new theory about language, which I developed over the past 10, 15 years with some colleagues. Now we think of language also like an evolution. Like you have the meanings of words initially and your actors in your text, and they change as the text evolves. You learn more about your characters in your text. So it's like an evolution, just like the evolution of a chemical system. And that's why this particular approach is so suitable for us. If you would try to do the analog to what machine learning people do, it wouldn't work on a quantum computer. It wouldn't work. It's much too data intensive.
Right. Let's talk a little bit about the book again and tell us how it came about and how it's doing and what the impact it's having on the industry.
So the book itself is a presentation to a broad audience to something which is called ZX calculus and was developed in 2007 by Ross Duncan, who's the head of software at Continuum, and myself. And initially, this was supposed to be like a high-level language for quantum computing.
Hmm.
Now in industry, it's used as a low-level language, which is very interesting. Its use is widespread. Its use becoming widespread. All the big companies are using it now extensively. And the compiler, which I was mentioning, our compiler ticket, basically the optimization, which is making your circuit as small as possible, uses exactly the techniques from the book. So, I mean, it's taken a while for this to kick in because people felt, I mean, for different reasons, because the category theory I mentioned before, because it's
Hmm.
pictures, and no people get suspicious about pictures. They don't think it's math for some reason. Well, as I explained, it's really rigorous math. So yes, now lots of companies are using it, and especially the photonic companies. I mean, I mentioned the biggest photonic company basically uses it as its main language. That's how
Uh-huh.
they write their papers now. So it's doing really well. And okay, last night, coincidentally, Carlo Rovelli, you may know from his popular books on physics and all that, he tweeted and on Facebook, he called our book fabulous. And
Excellent.
so our sales went up like they spiked a lot like overnight.
Brilliant, brilliant. Well, it is fabulous. And I think it's such a great contribution to this industry because, of course, as Doug opened, this stuff is just hard. And there are quotes that if you guys are like having that sort of a perspective on it, imagine what the rest of us do. So it is hard. And to make it simplified, I think is a giant requirement.
I mean, there is an important thing about inclusivity, like in quantum computing, it's going to be here and it's going to become probably an important part of technology. And what happened with AI is like when all the stuff broke through, nobody knew what it was. Nobody understood anything. And then suddenly you got a few companies dominating the world.
So speaking of that, speaking of quantum computing being an important technology, what does your crystal ball say, if it says anything, about when we can expect to have a real application do better than classical computers could do?
I mean, there's two different things. There is doing something a classical machine can't do. We're pretty much already there, very close. But it's not an interesting thing. Let's put it like that. Doing something interesting a classical machine can't do. That's a different question. Doing something interesting a classical machine can do at a commercial level. That's yet another question.
Mm,
Not just
right.
achieving it once in a lab. I mean, my crystal ball says, and I've been talking to our hardware people about that me and my team, with the things I was explaining, with the language stuff, possibly within 2 years, we could do something that is meaningful, that's
Mm,
significant. It has to do with natural language and asking questions about it. That would be very hard on a classical machine. We think we're going to be
brilliant.
there within 2 years, and that's going to be specifically on our machines because they are a good fit for what we are doing. that's nowhere near saying, okay, quantum natural language processing taking over classical machine learning or anything like that,
Right,
or,
right.
or is even useful for anything commercial. I'm not going to give my opinion, but I think the general consensus is it's going to be within this decennium.
Got it.
Okay.
So yeah, it's going to be in the 2020s. Okay, 1920s.
That's right.
Who knows? Who knows?
Bob, thanks so much for joining us today. Great discussion. He is co-author of Quantum in Pictures. That's the name of the book. It's on Amazon. I encourage everybody to at least look at the cover. As I said, one of my favorite pieces of cover art ever. And so thanks so much, Bob, and maybe we'll talk with you again soon.
Okay, thank you.
Take care. Thank you.
Cheers.
That's it for this episode of the @HPC podcast. Every episode is featured on InsideHPC.com and posted on OrionX.net. Use the comment section or tweet us with any questions or to propose topics of discussion. If you like the show, rate and review it on Apple Podcasts or wherever you listen. The @HPC podcast is a production of OrionX in association with Inside HPC. Thank you for listening.